for being here. So, well, as everybody here must know, that complex networks are a structure that lies somewhere behind regularity and randomness. So when you study networks, a thing that I like, well, what has been driving my research so far, and a question I'm raising is, what are the fundamental properties or building blocks of network, if any? And in that sense, what I mean is there like a way to extract some sort of structural dynamic of a network such that, taking into account these properties, you can fix all the all the higher level structural properties. So something that you, for instance, let's say community structure. So based on some low level properties, you can reproduce the communities that you find in neural networks, and also use these building blocks to, well, use them to predict the outcome or the time evolution of their different dynamical processes on these networks. So this is like a very broad question, and obviously we already have some answers about that. So we know that the degree distribution is very important, the correlation between the degrees, the activity in general is important, motifs, clustering, communities are something important, but I would argue that we still don't have the full picture. There are some, of course, encouraging numerical results. I refer to you to the VK series paper by Dima here. I think that offer very good insights. But I think the fact that we still lack a unique and comprehensive way to compare networks. So if I have two structures and I have to say, well, how different are they? How close to one another are they? The fact that we don't, well, to the best of my knowledge, we don't have like a very unique way to do that. And also the fact that we're still very limited in the analytical calculation that we can do. I think this suggests that, in fact, the answer is still incomplete. So, is there such a thing as the structural DNA of complex networks? Perhaps no. Perhaps this is the fundamental properties of complex networks is the fact that you cannot break them into the sum of some properties. But I would say that just the mere fact of looking for that will teach us a lot about these structures, these objects themselves. And also what I will explain in this talk is, well, discuss briefly, is how the work of trying to understand or find this effective structure has contributions to other fields that are of interest for other sciences. So I'm going to present two approaches that I think are very interesting in the sense of finding this effective structure. So I'm just going to explain about that, and then briefly discuss two applications that are actually on ongoing projects. So this is more like just to give you a sense of how I see the kind of contribution that I see that this quest can do to other fields. So first, what we have called the unending decomposition. So I guess everybody here is familiar with the K-car decomposition. So basically, the K-car is a maximal subgraph such that all the nodes are K links between them. So one way to establish in which K-car, which are the K-cars, well, you start with the small network here. You attribute to each node that has, like a membership in the one core, and then you start removing nodes that have like degree 1, you remove them, and then nodes that now, for instance, you remove these two, but then after that you get another one with degree 1, you remove it as well, until you cannot remove the degree 1 nodes. The remaining nodes, you assign them to the 2 core, and then you do that again with nodes of degree 2. So basically, the maximum value of K, the maximum core in which node exists, is what we call the coreness, and it's a measure of the centrality. So it gives you an idea how central is the node in the network. And it also, for instance, in the sense of, in the case of propagation of diseases, then it gives you like where you expect the disease to, let's say, the outbreak start in the periphery, then go to the center, and then reach the rest of the periphery. If it invades the whole network, then it gives you a sense of how at risk is a node, and with the inference you can have on the propagation of disease. So knowing how, knowing like the distribution of coordinates in a network gives you a sense of the distribution of the centrality. So how are nodes distributed in this concentric way of seeing the organization of the network. But if I give you these two networks here, so this is like a regular 10 by 10 lattice, and this is like a Kelly tree, but where there are links between the nodes that are right next at the same level and next to one another. And if you do the k-core decomposition of this, you'll find that each node, so each node is actually in the 2-core. And based on the k-core decomposition, you cannot differentiate these two structures that are obviously quite different. So basically, if we, well, that are obviously very different. But if we like just let's do the algorithm for that.
Isn't the first one is a 1-core and the second one is a 2-core?
No, because these ones are the two. They're just not easy to see. But like these two are connected, these two as well, these as well. The only one that don't form a triangle, and it's for the sake of the argument, are the one in the center, because otherwise they would have like a 3-core. So let's say that we do the k-core decomposition on that one, so we will remove like, well, there's no degree 1, so that's done. Degree 2, so we have these 4 ones here that we remove. And then we remove, and then we have like other degree 2 nodes that we remove as well. And you see that when we do the decomposition, we kind of follow the internal organization of the core. So basically, if we keep track of the layers at which nodes are removed, then we get information of the internal organization of the core, and this is what we call the anomaly decomposition. So this is nothing original, like layers of anomaly. And if we look then at the number of nodes in each layer, or the fraction of nodes in each layer, then we see that the Kelly tree that I've showed you and the lattice are quite different. So we have only 1 core. So this is one, I'm going to explain this figure later, but 1 core, but we see this is a similar figure here. We see that we have like an exponential decrease, and basically the property of the Kelly tree. And it is a square lattice, and this is similar as well, so not easy, but this is actually the linear growth, and then linear decrease, and then decreases linearly. So this is actually, you reach more and more nodes until you reach half, until you have reached half of the nodes, and then it decreases because you're getting into. So if we, for instance, this is like this is the onion decomposition of a subset of the World Wide Web. So what we have for each color, this corresponds to a different core, and all the points here are different layers in that core. So we see that just by comparing this, the decomposition that we have here with these toy models, we see that we can identify, for instance, a tree-like, some sort of, I mean, it doesn't have, means that it doesn't have clustering, but it's like a tree-like way of decomposing the core, or sometimes have something that is more lattice-like. So it gives you a sense. I mean, this is not very quantitative, but it gives you a sense of the internal organization of the network. And also, whenever there's a small change, so for instance, here there's a change in the slope, there's a small plateau. And whenever there's a change, it tells you that there may be something of interest, like a subgraph of interest. So for instance, in this small part here, what we found is a bunch of chains of the nodes that are connected to one another. So that would be like in a website, that would be like, when you've got sections where you read and then you get next page, previous page, something like that. And it's hard to see here, but there's like an agglutination of the nodes. And when you look at that, you find this very modular structure here. So then that would be kind of this index.html that then redirect you to different submodules that don't speak, that are of topic that are not that much related to one another. So the other decomposition gives you kind of a snapshot of the network, and it can help you to identify some subgraphs that are interesting. Also, it allows to define random ensemble, random network ensemble. So if I take the tree again, basically if I if I identify the nodes based on their degree, and I shuffle the edges, so basically I do a configuration model, I will get, so degree 1 and the degree 1, I will get something like that. This is one realization. So first we see that we totally lost the tree. We have like actually 4 components. We have degree 1 nodes that are connected to one another. That's something that you can find in the tree originally. And even if you take into the degree correlations, then you will get rid of these 2 components, but otherwise it will be something very mixed up, and you use the tree. But actually there's a way, based on the layers to which the nodes belong, to force, to define some local connection rules that are quite simple. So either they fix the number of links that nodes will have with nodes of with a greater layer, or it gives or it fixes like upper bounds and lower bounds, such that if you shuffle the edges, and based on that, you will always fall back on the tree, up to some isomorphism. And you can do that actually with less information than the correlated configuration model, since typically in neural networks, the number of layers scales as more or less the square root of the maximum degree. And just to give you an example, this is a bar grid from Polio. So we see that first, we see that if we would have only looked at the K core, we would have found 5 cores, and that's it. But now we know that, for instance, the first 2 cores, this one and this one, are more or less tree-like. But since the two inner layers, the 2 cores are only one layer, you expect them to be very tightly connected to one another. So this is some information. And also, this is simply like the same network where every edge are really interested in rewired on average 500 times, and you see that you get exactly the same thing. Now, in the first slide, I was talking about how these fundamental building blocks or fundamental properties would then explain higher level properties. And I think in this case, there's a few interesting things, but I think the most striking one is the fact that it can fairly well reproduce the distribution shortest path. So this is for one internet and a peer-to-peer network. And in green, we have a configuration model, so shuffle-based, preserving only the degree distribution. In blue is the correlated configuration model, so it's the enforcing the degree correlations. In red is the neural network, and in yellow is the ensemble defined by these groups. So it's not perfect, and if you wonder, the reason why there's some number below 1 is just because this is like an average over many relationships. But it gives you, this suggests that by taking into account the layers, you kind of stretch correctly the network such that you can reproduce that kind of properties. Something that, that's the case of associating, it's not possible. It's not too bad, but it's not that strict. Okay, also, the fact that these are only, this is quite, and I think this is quite nice because you can enforce local connection rules that only like neighbor to neighbor, but then you can reproduce some sort of mesoscale or macroscopic properties of the network. And since these are local rules, well, you can use, for instance, a generating function formalism to calculate like bound percolation of this ensemble. And this actually performs quite well. So this is a network of collaboration. So basically, this is the archive in which people are connected if we have cores of the paper. In red, these are this is the probability of keeping keeping the edges. So you remove with normalized. And this is the size of the extensive. The points are the real numerical results, so we just perform many percolation on the network in the average. In blue here, this is the correlated configuration model. In black, it's the message passing approach. And my sense, this is so far the state of the best thing we can do analytically. So it takes, this is still sort of a generating function formalism, but you kind of solve for every links. So you kind of take like the adjacency matrix, and you have like an equation for the probability for every link to the giant component. Whereas in our case, it's called the one here, we only have like the number of more or less Lmax times Lmax equations to solve. So you have less equations, and we found a way to include effective matter clustering. And we found that in this case, whenever for the whole range of the probability, we cover more or less well what we found in the network. So this is a network of 30,000 nodes, and these equations, like formally, are for a network that are infinite. So with an infinite formalism, you can still reproduce quite well what you find in the finite. So, but to be fair, I mean, this is an example that worked well. There are still some that don't work, that doesn't work, and so I mean, there's still some stuff to do. I mean, many of them work well. It's not just cherry picking, but there's still some work to do. We have thought we have. I mean, this is a figure I got like last Tuesday. So we still have some ideas to work on, and we have some ways to include the clustering even better. So I'm quite hopeful that we'll extend the number of networks for which this formalism works. So that's about it about the element composition. So basically, the effective structure in that case would be where the nodes are in the onion composition. How far are they from the core? Where are they between the periphery and the core of the Okay, so I'm going to talk about it quite quickly because many people here work on that kind of issue. So I think many of you are familiar with that. So the hidden metric space methodology is basically you assume that you have a network that you measure, that you work with, and there's somehow this abstract metric space in which nodes are, and where the distances between the node encodes the probability of being connected. So typically, the closer you are, the more likely you are to be connected. And this is interesting because since this is a metric space, the triangle inequality implies that we will find high levels of clustering. And it also gives a very nice geometric interpretation of the self-similarity. Provides realistic models of networks in which preferential attachment emerges from local optimization. So you don't have to know the degree of all the nodes to know whether you connect with them, but you're just based on the nodes that are close to you. And also, whenever you've got a scale-free distribution, it can be shown that the natural geometry for this network is the hyperbolic disk in that case. So if you know, basically an hyperbolic geometry means that distances increases exponentially between two lines that are. So just to give you a feeling of that, so this is the hyperbolic disk, center in the cross here, and in red you see a circle with the same radius, but centered around that one. And the lines show you the geodesic. So this is the smallest, the shortest path, shortest distance between these two nodes is 2 photos. And because of that, well, you expect nodes that are close to the center to have a higher degree. So there's like a lot of stuff done from the theoretical side of that, but I think in the context of an effective structure, what's interesting is the fact that we can map the topology of a network to positions in the space. So then the position in that space act as this effective information that then using geometric models can allow you to produce statistically the properties of the network. And for instance, we have done that for the international trade. So basically we've done this embedding. So the embedding is simply, you take the network topology and you just find, using Monte Carlo simulations the best, good coordinates such that your model is likely to reproduce the structure that you want to store. And so we've done that for international trade between countries for over 14 decades, so since like the 1870s. And then what's interesting is that as you look, as the years go by, you see, for instance, well, this is 2013, but you see, for instance, the British Empire then dissolve into the Commonwealth. You see the French colonies, appearing, but then staying very close to France because they are still very dependent economically with these countries. And you see the rise of China, for instance. So then the information encoded in the coordinates help us, for instance, understand the kind of things that I just explained, but also look at whether or not PTAs, so preferential trade agreements, have had some effect on how close trade-wise, how close are to different countries. Another nice example is this can be used also to identify new biochemical pathways. So this is for E. coli. So these are basically the reactions, these are the metabolites. And when you do the embedding, based on the information that we have so far, then you can look at whether, well, if two metabolites by interactions are close to one another but they are not connected, you can say, well, maybe they are likely to be connected. And then this kind of guides then like experiences in the lab to just see if these make sense or not. And this is something actually that I've done. This is not my paper, but this is something that I've done. And finally, a nice application as well is a way to provide efficient routing protocols. So this is a map of the internet, again done by people. So basically, when you want to forward some message between two different servers or autonomous systems, you kind of need to know what the map is to know to whom you need to forward the message, which then will be forwarded to another one until the target destination. But one very nice property of this kind of models is that the geodesic and the shortest path are very close to one another. So basically, if you just follow the shortest distance, you're very likely to follow the shortest path. And if you follow the shortest path, so the fewer hops you need to do, the more likely you are to, the more likely your package is to reach the destination. So in a case where internet is growing, this is like, well, let's say that once you know in this case, you don't need to know the whole. You don't need to know the whole map of shortest path. You just need to then forward your message to your neighbor that is the closest to the target, and you know that you can be confident. I mean, there's some caveats, but you're confident that your package will reach the destination. This is a quick overview of this methodology. One thing is, everything has been, not everything, but what I've presented here has been developed for undirected network, unweighted networks. And in the case, for instance, of trade, of airport networks, of the brain, the weights matter. They bring you an important information. So in the case of trade, obviously, the trade between Canada and the States are different than the trade between the States and whatever other country. So the volume is important to understand the closeness between two countries. Also in the case of the brain, because we cannot have a precise neuron-to-neuron map of interaction, usually we are based on the regions, and then the weights correspond to the density of fibers. So it gives you a magnitude of how connected are these two regions. And for instance, in the case of the trade here, what we had to do, since we didn't have the weighted formalism at this point, was to filter the different, all the weights to only extract the significant ones. So we have something that is meaningful, but still incomplete. So the idea was to develop, because to do the embedding, you need the model. So the idea was to develop a model of weighted networks in that kind of in a metric space. in order to eventually do the inverse problem and get the mapping using the information encoded in the weights. Also, I mean, this is like the reason for kind of application, but still, from the theoretical point of view, it was interesting because the weights are not trivially coupled with the degrees. So usually the strength, which is like the weighted degree, usually scales. Usually doesn't scale linearly with the degree. So there's some sort, and this is, I mean, you cannot. There's something non-trivial. And also, it's interesting because it gives us like a new perspective on the interactions. For instance, the rich club, if you base only on the undirected version of the network, you can observe a rich club, and then if you look at the intensity of the interaction, you can see that these are connected, but they don't interact that much. So is that it's still a rich club? So I'm not going to show you the equation, but basically what we did is, very roughly speaking, kept the same model for to explain the topology. But if we want to have like a geometric interpretation, we added masses to the nodes. So nodes have now masses, and the weights of the links are based on the masses, the particular masses, and dependence on the distance. And I mean, there's a way to figure out with the way you need to couple with the metric space, and there's a good way to select all these parameters. But what we find is that we can fairly well reproduce many properties of these networks. So this is the degree distribution. This is the clustering dependent on the degree. These were already good in the unweighted network model, so that's fine. But then we found that if we fix this relationship that I showed here, and just adjust somehow, this is not witchcraft, and there's a good way to do it, but the noise of the strength distribution, then for instance we get for free the weight distribution. So I mean, this is a model that assumes continuous weights. So then this is a network where the weights are finite. So this is one of the small disagreement here, but still you find that there's only one way you can distribute the weights so that you can reproduce the relationship between the strength and the degree and reproduce the strength distribution, and it's actually the same one as in the network. And also we find that this is the disparity. So disparity is just a measure of how heterogeneous are the weights for each node. So how are the weights distributed more or less uniformly with all my neighbors, or do I have like only one very strong interaction and the other one is the interaction is very weak? And you find that they are uniform only if you 1/k would correspond to a very uniform distribution. So whenever it's a bit higher, then you correspond that there is some sort of heterogeneity, and still we find something that is, for that kind of model, quite good agreement. So when I was talking about how simpler building blocks can explain higher level properties, this is what I mean. And also we did the same thing with the brain and get the same quality of agreements. The only thing is maybe this disagreement here, but this was known already because the way we do the models, this is not natural. The fact that you have a drop for low degrees is not natural, but this is something that could be included as well. So this is not a drawback, this is just the way we decided to do it. So basically this is one approach. Now the next step is to do the inverse problem, as I was saying, and then try to, for instance, redo the volume of trade, see if the fact that we take into account the weights changes a lot or not the map that we can make up. And also something that I'm just interested to do is use that to somehow get like another way to map the connections within the brain. So that's about it about the two approaches. So application. So so when I said that it was useful to, I mean, I argue that it is useful to do that kind of research because it has some good repercussion about other fields. Well, this is one of them. So basically, in this case, this is not the effective structure itself that was useful, but all the mathematical tools that we developed that we could use to apply to the sexual transmission of Zika. So basically, well, you all know that Zika is transmitted by mosquitoes, But there's also a chance of, if I'm infected, usually I may not have symptoms at all, but then through sexual contact, I may transmit the virus to my partner. And the peculiar thing here is that men are a lot more likely to transmit the disease than women. It's actually about 10 times more likely. And what we've been able to show is that the fact that you have this asymmetry in the probability of transmission, using very simple models, you actually have this double transition in which you will infect the men having sex with men community. So people that are, both partners are very likely to transmit it. And then at some other point, you will infect the rest of the population. And there's a lot of discussion right now as to whether the sexual transmission of Zika poses a threat or not. And many people, when they do like the average over all the population, they're like, well, the threshold is here and we're here, so we're fine. But what we argue is, well, you may have a community that typically does not get tested because one of the, other than maybe have a fever a few days, the main consequence of being infected is the, I call it in English, but like the, when you want to have a child, like they have like a microencephalosis, I think it's called. So you have a community that doesn't have reasons to get tested, obviously, but still that is overcritical. So they are infected and they have like this subcritical spillovers in the rest of the population. So you still may be able to drive. It's not like going to be a large scale epidemic, but it's going to be like localized and then having spillovers in the heterosexual population because of the asymmetry in the probability of transmission. So it's a very simple model, but all the tools that we developed for the effective, for the onion composition and the preparation, we've been able to use it. And it's actually really nice because this is one of the first time, I think this is the first time, that we have an analytical description of, I'm going to put my quotation mark, double phase transition. So this is not exactly a double phase transition because once you get the parameter not zero, then you can have another infinite cluster. But still, when for instance we look at the size of the clusters, so this is the number of nodes in each component. So this corresponds to the first transition here, so we get the power law that we expect in general. And then the second one, we still have a very, we're like almost 3 or 93% the power behavior that you will find in the phase transition. And the cutoff here, just because since you have like already a giant component, if your cluster gets too big at some point, you can connect it to the one and then you lose the transition. So this is one application to Zika, and the other one, I want to stress that this is very preliminary. This is something that I've been doing for like 6 months now, and something I want to do in future collaboration. But basically, okay, so two small projects. The first one is we know when we extract the connectome, when we extract the connection between the different regions of the brain, you can have the position. And you can look whether or not the connections are congruent with the topology. So in other words, if when you follow the shortest path, when you forward messages, this is the same thing as I was speaking before. When you forward messages to the closer your closest neighbor to a target, what's your success rate? How likely will the package get to the target? And basically, when we use the coordinates that we have for the connectome, so basically the coordinates in the brain, one found more or less, there's a lot of caveats here, of course, you see, but we got 2 regimes. The first one is like non-mammal and mammal, let's say. So the more evolved the brain is, the more likely you are to find a neighbor that is close to the target. The more success rate the higher the success rate will be. But one interesting thing is that even if we don't have, when we don't have the coordinates, but we still have the connections, we can do the embedding in the coordinate space, And we find that in the hyperbolic space, the success rate is always close to 1, even if the distribution is not polar. So the hyperbolic is not necessarily natural space, but still we find, in this case, we find that we improve greatly across all species, and we increase the success rate of 2. So the working hypothesis right now is just that probably maybe the degree has an important role, because in the degree has an important role in the probability of connection, so in the network. So we know that the distance plays a role, but maybe the connections are more likely to be done with nodes that are already well connected. But this is a working hypothesis, just to give you an idea. But then you can see that this is the point to show you that is, you see that all the tools that are developed for the images-based formalism can be used then, can be applied to neuroscience and studying the structure of the connectomes to see if there are some universal principles that all the nations. And the last one is something that I'm going to start at the moment. Kind of a recent one idea that I'm just throwing out here. But when it comes to infer connections in the brain, there's like 2 general ways to do it. So you've got the structural connectomes where you, through a specific kind of imaging technique, you follow the fibers. So you literally follow the anatomical connections between the different regions, and you know the density of them. So you know literally how different regions are connected to one another. The other one is called the functional connectors, where you have the activity of different regions and you correlate them with one another. So these regions are highly correlated when one is very active and one is very active as well. And one open question right now is how to use the functional information to infer the structural one. And something that we want to try is to convert these correlations into distances. So the closer you are, the more likely you are to be. Well, sorry, I'm again. So basically, we know generally that if 2 regions are correlated, they are likely to be connected. This is something that is accepted so far. So the idea is if we can translate the correlation in the functional connectome into distances, and then find the sort of an embedding using these distances, can we then use the generative model to quantify the probability of new connections, of connections that are not measured, but like can we quantify the probability for different regions to be connected as well? So this is kind of the general idea. So that's it. Thanks for the attention. This is work that has been done with many people, so I would like to thank. So for all the hidden metrics-based target systems in Barcelona, the annual competition has been done with George Rochelle and Robert Friend from SFI, now at in Boulder, Colorado, now at the Institute for Disability in Seattle. And the Zika projects are done in Laurent, Robert Friend, San Torpino in Vermont, and Benoit House in Disability. So thank you very much.
So, time for question. Yes, sir.
So for the embedding for the region network, so how do you decide the coordinate? Do you decide the coordinate just based on the degree, or you decide the coordinates based on the degree and the weight together?
For the embedding part,
Yeah,
you're gonna choose a coordinate such that the weighted model, like the network that you with the weights that you observe is the most likely to be is the organism that is the most likely to be generated by the model.
So my question would be is so the old algorithm for embedding without the weight. So you cannot use it for the degree distribution that has parallel gamma smaller larger than 2. So, but for many weighted networks, that's not the case. Many of them they are smaller than 2. So you cannot use the the one that only works with degrees anymore. So is a new algorithm can deal with those kind of situations.
Well, actually, something I didn't speak here is that you got like when you use the hyperbolic this is kind of the purely geometrical model. But there's a way to do it as well, where instead of having like a radial coordinate that corresponds somehow like in a way to your degree, you have like a space that is like a circle, for instance. So you have like the angular coordinate and then a mass, and the mass corresponds to your expected degree. So when you go back to this Newtonian kind of way to do the models, then it doesn't matter what your distribution is.
Okay.
So it's
Okay, so you can work with any degree.
yeah. It's just that in the hyperbolic, I think it's nicer. It's just such a show.
Okay.
Let me ask you a follow-up question on this. So as far as I understand the weighted model, if you throw away the weights on links, it's going to be equivalent to the unweighted model. So when you embed the weighted network, do you use weights for the maximal likelihood estimation, or do you use just unweighted version to embed?
And use the weights as well. So I mean, I would expect. My guess is that the coordinate that you will find will not be that different. But it's kind of the degree, the fact that you have a connection gives you some position, and then the weights come to fine tune the position. Or maybe if the weight is so weak that you just disregard more or less 15 degrees, disregard this link, and then maybe it's going to change the position more. But I'm not expecting to find maps that are they're a bit different, but it's not going to be totally different.
I didn't fully read your linear communications paper, but I read the archive version of the paper earlier on. Do you have the on the weighted extension? So, but do you have the code available for weighted embedding?
So it's a work in progress.
Okay, so you're working on it.
Yeah.
All right, thank you.
This might be relatively naive about the process, but I'm wondering about how the space itself changes. Like in the example of trade, you said that you could see China becoming a little leader in the British Empire fracturing. That changes the actual metric space, doesn't
It
it?
changes the position in the metric space.
And then their density or their mass is also changing too, right?
Yeah.
And so, do you see that as as the space itself is changing, or the nodes, by virtue of changing their properties, are changing the space?
Well, the only change that you have in the space is the fact that your range is going to grow with the number of nodes. And this is more or less just because we fix the density. We have like a free parameter, which is the density that we fix. So the density is, I would say that the density is there. So it's like something that exists that is there. And then we position the nodes based on the connection that they have. So if over the years the connections change, then the position will change, but not the space itself.
Okay.
It's not like
So I'm just wondering, like, when you're inverting that and trying to generate some process that can mimic what happened, are the nodes kind of making decisions about where they're going to link to next, or is there some strategic aspect to their behavior?
Well, in what I presented, no. The nodes are there, and you connect to other nodes that are within a given distance. And then you can smooth the transition so that you can calculate the clustering in a Fermi Dirac kind of way. But in what I presented, there's nothing like strategy. You did another paper about there's some Nash paper, but I don't remember exactly how much strategy was involved.
Yeah, so I have a question about these algorithms, well, routing in the brain, basically. So I guess that the Euclidean embedding is just the embedding of my brain in the three-dimensional space. And then the other embedding is your weighted embedding, I guess?
In that case, no, it's the...
Okay, it's just the unweighted embedding.
Yeah.
Okay. And then, so geometric routing in the hyperbolic space was extremely efficient, and routing in the Euclidean case was not very efficient. But how because you did the maximum likelihood estimation, right, to get the hyperbolic embedding.
Yeah.
So what was the likelihood of your brain being? Because hyperbolic routing in general is extremely efficient.
Yeah.
So the question is not whether or not this probability is 1, because it will be always 1 if you have a hyperbolic graph. The question is how likely is my brain to be a hyperbolic graph?
Yeah, that's actually a fair question. This is something that I was still trying to see if this is just an artifact of the hyperbolic. I would say that since the linear distribution are exponentially parallel, then the hyperbolic geometry is not the most. I mean, you do the optimization up to a point because this is not the natural embedding.
Mm-hmm.
So is it? So yeah, this is actually one of the possibilities that is just an artifact that you optimize.
But could you give us some sort of order of magnitude of the maximal likelihood that you got for your embedding? Because you had to compute it, right? You had to maximize the likelihood. So what was the eventual likelihood? Are we talking about 0.0001 or we're talking about 0.1 or?
That's a very good question. Well, because we don't typically in that kind of things we don't evaluate the quality of embedding based on the likelihood, like the absolute value. Look, for instance, if we like in the model that we use to do the optimization, we for instance use the typical quality connection. So this is kind of this Fermi Dirac more or less. And then you look at once that you have the coordinates and you generate a bunch of models, you look at whether or not you respect connection. Or also, since the position in the relative corresponds to a function of your expected degree, then you can look at, does my embedding give me something like an expected degree for each node that is linear, like that corresponds to the degree in the actual. So this is how we do the quality assessment.
Yeah.
This is not like the absolute value of the embedding. But yeah, I can say.
Okay. Well, please.
What's the difference between onion decomposition and keyboard decomposition?
Sorry,
What's the difference between onion decomposition and keyboard?
the onion includes the K-core, but includes also the way that this is a very algorithmic definition. So it's like how do you remove the nodes when you establish which node and which node? So like if you are the 3 core, for instance, you're gonna start removing the 3 nodes. But then the fact that you remove these ones, then you have other 3 nodes that you need to remove as well. But because they are removed in the second place, like on the second level, like in the second pass, you know that these ones, yes, they are in the 3 core, but they were connected to the ones before that. So it kind of gives you a way to information within the code. But all the information, if you sum over the layers within one core, you get the information.
Okay, so let's take again.